All right, welcome. I would encourage you, either now or sometime during the talk, you might want to spread a little bit closer to the screens and towards the front. There is some live demo material, and while I've tried to make the text large, the screens are not as large as the room is, so you won't hurt my feelings if, while I'm doing that, you start to migrate towards those points, but just a heads up for that. So a little bit about me. I'm a software engineer at Braintree Payments. We're a sponsor, and I'm on the database team, as you might not be surprised. I've also recently become a Postgres contributor. A little bit of background on just general setups and also ours. Postgres clusters are often deployed with at least 2 nodes in a physical replication scenario with a primary and a synchronous replica. We do more than that, but that's the most minimal configuration. Typically, availability of nodes in that physical cluster is managed automatically by some kind of control scripting, right? So in our case, we use Pacemaker and CoroSync to manage failovers. But before Pacemaker is allowed to promote a replica, it can fence or stoneth the primary via power distribution unit control, so it actually hard powers off the box. And our reasoning for that is that we would rather take an outage than suffer a split brain scenario like we'll investigate today in this talk. So what actually is a split brain? In a cluster of database nodes, a split brain occurs when, usually due to some kind of network partition or maybe operator error, multiple nodes end up believing that they are all each a primary node or the primary node. And we might kind of think about it more formally like this. Suppose we have this timeline of operations where we have a primary and a replica. They're both processing operations 1, 2, and 3 here in this diagram. And the replica looks exactly the same as the primary because it's just following the changes on the primary. It's not taking writes itself. And then some kind of error happens. Network partition maybe say at this yellow line. We promote the replica, and now we have 2 different primaries. And instead of having the bottom one here, now primary B, following what was the only primary before, it's now processing events that are different than the original, and they've diverged. A little bit of a sidebar on high availability configuration. Unless you absolutely value uptime over data consistency, then if your scripting fails to fence the current primary, you must also decide to fail to promote a new primary. Now, in reality, understanding trade-offs between availability and consistency is the important thing here. It's my personal opinion that it's too easy to assume that you would prefer uptime to data consistency. And in fact, some tooling like Vitroni, I think, actually explicitly makes this choice by default. But data inconsistency, for example, a split brain like we'll look at today, can be extremely painful for your business. So know how your setup works and what the trade-offs that you and your business are comfortable with before you make those decisions implicitly. But suppose you have all that set up, you've made the choices that I think are correct, and your fencing fails, so your primary is still up, but that scripting reported success, and so you promote a replica into a primary scenario anyways. Well, in that case, we have a split brain, even though we tried to avoid it. Which isn't fun, of course, in a production scenario, but it is kind of fun for this kind of presentation. Another sidebar, so a colleague of mine noted in Slack after I had presented this talk to them that in the same time slot as this presentation, there is a talk going on right now about setting up high availability Postgres correctly in Kubernetes. And then he included this meme in our Slack channel. But all joking aside, why do I think that knowing how to troubleshoot and recover from a split brain is a valuable thing to learn? It's not just a fun talk to be at. Well, even with all of the right tooling, and you should have the right tooling, but even with all of the right tooling, the longer that you run and the larger you grow, something and probably more than one thing, maybe even more than one thing at the same time, is going to bite you in production. So I believe that it's a good idea to think about the kind of potential failure modes that you might encounter in advance and have an idea of how you might investigate and respond to various ones and what kind of tooling is available. you don't want to be trying to find out what kind of tools Postgres has available when you're in the moment of a scenario like this. I've also read postmortems from more than one company of fairly high-profile incidents, and I won't name names, but you can, I'm sure, search for those online and find those postmortems. And so clearly this happens even to well-intentioned and very intelligent people. So we've split-brained. What do we do now? Well, first, we want to investigate what's changed on each primary since that split occurred. And Postgres conveniently encodes all of our logical changes in the write-ahead log, so that's the place we would naturally go to try to figure out what's happened. And our first thought might be to use the logical decoding, but you can't replay with logical decoding. You can't go back in time. So unless you took the kind of absurd step of setting up, say, a replication slot that doesn't advance each day, and you could always go back 24 hours, I suppose you could do that, but it would be kind of a weird setup. Alternatively, Postgres comes with this utility called pgwalldump, or in previous versions before the big rename from xlog to wall everywhere in the code base called pgxlogdump. And the docs for pgwalldump say that it displays a human-readable rendering of the write-ahead log, but go on to claim that it's mostly useful for debugging or educational purposes, which I think is actually underselling the value here of this tool. But let's start by trying out here a little bit of what we can find out with the with this utility. So what I'm going to do here first is boot up a Docker container setup that I have. And we spin up two different Postgres nodes, a primary and a replica, with physical replication between them. I've also inserted some rows and updated a few rows just to give us some seed data so that our wall isn't entirely empty. And we're going to go ahead and log into the primary here. And we'll start by looking at our Postgres data directory. And specifically what is in this directory, pgwall, which is where our write-ahead log segments are stored. And we see these 16 megabyte files here that look like they're in some kind of monotonically increasing sequences of the file names. And that's where our write-ahead log is stored. So if we actually use this pgwalldump utility and pass it a path, which is our pgwall directory, we start with that. And it will complain because we haven't told it where to start. So we'll go ahead and copy one of, I'll just take the last segment here and run it with that as the start. And we get this mess on screen. Remember, the doc said that it's human readable, and I think that's technically accurate, but there's a lot of information here. So again, this is a tool that you want to be familiar with if you're going to use later. If you're going to use in a failure scenario, seeing this kind of thing and understanding what's there now is better than digging through this in the moment. So let's actually take a look at a couple of these things. So I'm going to start at this insert record right here. And I've highlighted on screen. The left-hand side starts with this column with a label RMGR, I believe record manager. And then it tells us effectively the category or type of record that we're looking at here in the write-ahead log. And the convention wireless thing keeps popping up and annoying me on my screen. So this is a heap record. So we can deduce that we're modifying the heap, no big surprise there. It gives us lengths of the record. Where I think things start to get interesting, though, is we see in the middle of the screen here tx colon and then an integer. And that's our transaction ID. So the transaction ID, of course, is the base of how Postgres implements multi-version concurrency control. And we'll note that because our server is concurrent, no surprise there either, these transaction IDs are not monotonically increasing in these records. There's a bunch of records here with 572 and then 573 and 4 and so on. But then at the bottom, you might see that there's 571 for several records. After that column, we have the LSN, or logical sequence number, and that is monotonically increasing because that's just an index into the write-ahead log stream. It also conveniently tells us what the previous LSN was. And then it gives us the kind of most meaty part of what comes out in this output, and that is a description of what this record contains. So in this heap record, we see an insert, which we can easily understand, but then we have a lot of abbreviated things. OFF here is really offset, so it's telling us that at offset 11 in block or page 0, there's an insert occurred at that point in the heap. That offset and block also we'll look at again later as the CTID, or the physical reference to a location on disk that Postgres uses to reference an absolute physical row. But then we have this rel and 3 numbers separated by slashes that isn't immediately obvious what it is. And I can tell you what it is, but I actually think that it is more interesting to log into our server and find out for ourselves, because it turns out that all of these things are available in the PG catalog tables. So that first number there is 1663, and it is actually the references the OID of the PG table space table. And if we select the name of that, see we have 2 different table spaces here, and then if we add where OID equals 1663, we'll get this in the default table space. Now, probably most of you in the room don't rely on multiple table spaces in your Postgres cluster setups. I think that they're generally more common in cases where you might have fast and slow storage. But it's really a way to say, on a different volume on disk, I would like to store tables, as opposed to just a single directory. But we just have one here. So that's interesting, but it doesn't necessarily point us at exactly where we need to go. So let's look at the second number, the 16384. And that happens to be the OID of the database involved. So let's find out what the name of the database is that we're referencing. And we find out that, in fact, it is in the database that I've conveniently called demo. So let's go ahead and connect to that database. And the final record here that has unhelpfully scrolled off of the screen, or the final number is, for this insert record, is 16387. And that number is the table name So we can select from PG class with our OID, and we find out that it was an insert into the items table. So all of those numbers uniquely identify a table. Now, this last query that I did, some in the room might know is slightly incorrect. It turns out that really what I should do is change OID here to rel file node. And we'll get the same row for now. If you truncate the table, for example, it will rewrite the table. There'll be a new rel file node on disk, and the OID and rel file node will no longer match. So a little bit of a caveat there. So let's go back and look at this wall output a little bit more. So we looked at an insert record. Let's go ahead and look at a B-tree record. So our manager type here is B-tree. And of course, we're modifying an index. And our description tells us that it's inserting a leaf, since our tree, of course, has roots and then leaf nodes. So it's inserting a leaf at offset 11 in block 1. And we could do the same thing, but we won't take time to look at this rel number and find out that that last number 16394 actually refers to the primary key index on this table. And then if we if we come down, or if we go up one here and look at commit, the final thing that we'll look at in this output is the manager type of transaction. And we see that we actually get a commit. And at this point, of course, these inserts or updates would actually show up and be visible depending on your transaction isolation level. And it conveniently gives us a timestamp to give us a rough idea of when this occurred also. Yes?
The rels are all same pattern, right?
Yes, yeah. They're all OID of table space, and then OID of database name, and then rel file node of the PG class entry. All right, so let's get back to our presentation. We'll come back to that output in a bit. So let's zoom out a little bit from that level of detail. We've looked at the write-ahead log dump, but there's a lot there, and if we're actually in a very high concurrency server, of course, we might have gigabytes of this wall. So how do we know when to start reading in that output? Because I don't want to have to troll through all of it for all of time. And if we look at the logs from our server after doing a promote on the replica, we'll see output that looks like this. Postgres will tell us that it received a promote request. Since all of this, of course, is manual, where manual might be a script, but it's something firing off a command. Postgres isn't deciding to do this on its own. It terminates receiving wall. Again, not surprising. And then it tells us that we have an invalid record length, and it gives us an LSN. And tells us that the redo is done at a different LSN, tells us the last completed transaction, and then selects a new timeline. Now, timelines are a feature that was added in actually quite a while back, I believe in the 8 series of Postgres, that are basically designed so that when this promote happens, we don't accidentally then say try to apply the write-ahead log that will be generated from the newly promoted primary to an old primary, because that would not make you happy and would almost certainly mean that your database would be corrupted. So we have these two indexes into the wall stream to guide us. And the first one is, or second in the actual log output that we looked at, where it says redo done, is the last successfully applied record from the primary, which means the one that it had an error processing is actually going to be the first record that's different on our 2 different primaries. Now, wall positioning numbering takes a little bit of explanation also. A position or index into the write-ahead log stream is really a 64-bit integer, but Postgres tends to print it as, or always prints it as far as I'm aware, as 2 32-bit hex encoded values that it then separates visually by a slash. And also, helpfully, but also sometimes confusingly, trims more than one leading 0 on each of those 2 values. So for example, this LSN that we've been looking at actually expands this longer hex string. And Postgres includes many functions for working with write-ahead log positions and telling you how to map those LSN positions into segment file names on disk to make this easier. And you can find a more detailed explanation online at this blog post that I referenced. But a quick summary for at least some information that's relevant to this talk. Write-ahead log file segments, a little bit of detail here, as distinct from write-ahead log files, which are logical and encompass multiple segments, are named on disk with this 24-character hex string. The first 8 encodes the timeline, the second 8 encodes the logical wall file, and the final 8 encodes the offset within that logical wall file. So for example, if we have this LSN that we've been looking at repeatedly here, assuming that it is in timeline 1, then we see that the first 4 digits here before the slash, the 3583, end up showing up on in that middle 8 characters in our file name. And the first 2 characters after the slash end up at the end, or the final 8 characters. Now, like I said, it trims leading 0, so you have to be careful if, say, the A had happened to actually be a 0, it would have gotten dropped and only 6 would have shown up in the file. So it's not necessarily the first 2 characters after the slash, but that's why there's functions to actually help you figure this out. So we want to investigate a split brain, but first we actually have to have one to investigate. And so we're going to manually simulate it by just promoting the replica that we have here in our Docker setup. So if you'll forgive me, I'm going to copy and paste these commands in a separate window here just so that I don't have to type at an odd angle here on stage and likely make lots of typos. All of this information, by the way, is available in a GitHub repository that I'll share a link to at the end of the talk. So if these commands, if you don't have time to write them down, you can look at them later. So we actually don't want to do that right here because this is our primary. So we're going to log into the replica, and we'll use PG control to promote our primary. And earlier I made the claim that we could look at the logs and see how that promote occurred. So let's actually prove that that's true. It would help if I lest that file instead of trying to cd into a file. So in fact, we see effectively the same kind of thing that I had on screen before. We received a promote request from our pgctl command. It stopped receiving wall from the primary, tells us the previous or the next record, what will be different in the last record that applied cleanly, and so on, and tells us that it selected a new timeline ID 2. And we can actually see that that timeline ID matters by looking at our wall directory. And we see not only that we have this 00 repeated zeros 1 timeline 1 files, and then we see a new file has been created that has a prefix that starts with 2. And so we've switched into timeline 2, and wall segments are carrying on that new name. Now, while technically we have a split brain at this point, it's not a particularly interesting one since we haven't changed any data on either side. So the next thing that we want to do is remedy that error. And we'll go ahead and create a little bit more of an interesting scenario to look at. So on the primary, I'm going to insert one new value. And then on the replica, I'm going to both insert one row and update one row. So we're going to insert into items one row with a name of Zag, and we'll update one row, which happens to be the first row, by the way. And so we can go ahead and see that, in fact, these updates have made meaningful differences, and in fact, the servers have diverged if we run a select on both sides. And the screen is a little too small here to show all of it, but we see that that last record, for example, has both a different primary key value and a different text name value. And just kind of file away in the back of your mind that we have both an update and an insert that we did here, because we'll hopefully come back and find that out later through our investigatory tools. So back to our presentation. So we have a divergent server, and we know that we can look at PG wall dump output and see the kinds of operations that have occurred since the divergence. But that output so far isn't overly helpful at the application or business level. Now there's a minor exception here. If there were no commit activity on one side, on one of the two primaries after that divergence point, then we can safely conclude that there's no functional divergence, right? Because if nothing is committed, then nothing is visible. And even if you've run inserts, it wasn't real because it hasn't committed. So if there's no commit activity, then you lucked out and you can stop here for the most part. But that's unlikely, and we really want to know domain or business impact. Like, we want to know the kind of tables that were inserted into and what the values were on our diverging primaries. So how do we determine that? We will zoom in on each of these 3 steps more concretely, but we're going to start by identifying all of the transaction IDs that were committed after that divergence occurred. We're going to try to convert those write-ahead log operations that we saw in the PG wall dump output into actual tuple data, and then we'll talk a little bit about manually investigating that information. So first, we'll identify all of the transaction IDs that were committed after the divergence point. Now, this is the simplest step in our process because we can just use these handy Unix utilities, grep, awk, and sed on the PG wall dump output and get our list of transaction IDs. But converting the write-ahead log operations into tuple data is a bit more complicated. There's no Unix utility for this. So first we have to dump the relevant write-ahead log output. But consider this sequence of operations. Suppose we open a transaction, we insert a record, and then our split brain occurs, and finally we commit that transaction on the primary that we were connected to. If we only look at write-ahead log output that starts after 3, we'll miss this insert. We'll see a commit and think that it was for an empty transaction, and that's not particularly helpful because this actually is a difference between our two servers, even though the insert occurred in theory, and in fact this insert write-ahead log record applied to both sides. But it isn't visible on both sides, so it's a functional divergence. So we have to start far enough before the divergence point to include all transactions that were in flight when the divergence actually occurred. Yes?
So the DDR operation doesn't commit also if something else happens, like somebody updates the table structure in the same session, truncates a table.
Oh, if you truncate a table, I'm not.
Isn't that a commit operation for the previous transaction?
No, at least as far as I'm understanding the question, you do need an explicit commit.
Okay, so this is an Oracle way of doing it.
DDL is transactional.
So after we've done that, like we've captured our write-ahead log output from a little bit before the divergence point, we'll parse out the transaction ID, the rel file node that we talked about earlier, the block on the offset, or CTID, which is the physical location on disk again, and the logical operation type, like inserts and updates and so on. Additionally, while we're parsing those fields, we have to keep track of a chain of CTIDs to find out the most recent logical tuple for each change that occurred. So consider this sequence of operations. Suppose our split brain occurs, and then we update a row where the primary key is 1, and then we update the same row again in this transaction, and then we commit. Well, because of Postgres's multi-version concurrency control, this will result in 2 physical rows on disk, but only one of them is visible after this, right? And only one of them do we actually care about because it's the final state of the logical row on disk. So we want to track that the row generated at step number 2 and the row generated at step number 3 are actually logically connected, and only look at the third one, or the last one. Finally, we can use that information to query the diverging primary to find the actual data inserted or updated, because we can actually query based on that CTID value. It's a hidden column in your Postgres table. Unfortunately, we won't be able to easily figure out anything that was deleted. Maybe you could if it still existed on the primary, no one had done deletes, there's no vacuums that occurred, and so on. We might be able to find it there, but that's a bit iffy. We also lose intermediate states of rows, both the example that I gave in last slide and if 2 different transactions affect the same logical row. But even so, we can get a pretty reasonable view of the activity or the state difference between the 2 nodes after that divergence has occurred. So that all sounds intriguing, but again, the proof isn't seen, it actually happened. So this is where we'll get into the Ansem custom scripting that I referenced in the abstract. So the first thing that we're going to do is actually stop Postgres on what was our replica. And then earlier when we looked at the wall segments, and you can still see it at the top of the screen here, and you can see there's a segment that ends in .partial. That actually got flushed out when it switched to timelines, and has the same name other than the timeline component of this file name as the next segment following it. But it does contain real information. And PG wall dump will ignore those .partial segments. So we're going to cheat a little bit, and we will just copy that partial segment into the same named file, but without the .partial at the end. PG wall dump also can't file timeline switches. And so we actually have to output in 2 steps. We'll output first from the records from the segments that are relevant in timeline 1, You can ignore these errors, by the way. That will almost always happen because PG wall dump is just saying that it found a record that was no longer valid, and that's really the end of the write-ahead log stream. So we've got that, and we'll then also do the same thing, but for the file in timeline 2. And if we look at this file that I've called fuzzywindow.txt, you'll see that the output looks exactly like what we got from PG wall dump. Next, we want to determine the LSN that actually kicks off our changes between the two. And so we can just grep the logs for this terminating wall receiver, and we find our invalid record length at this particular LSN. And we'll go ahead and plug that into our next command. So we're going to run PG wall dump again here. But this time we're going to provide a specific LSN within this file to start, and that's this 0/4004D78. And we're going to grep out all of the commit records and parse out their transaction IDs. So if we look at this file that I've generated, divergent TXIDs, we'll see 2 transactions, and that makes sense because remember earlier we did an insert and an update, so we have 2 transactions that have changed. So this so far seems to logically match up what we expect to see, right? Then we'll go ahead and take that information and generate our relation and CTID chains that I mentioned earlier. And if, again, this scripting is available online, so I'm not going to jump into the Ruby code that I've written here, but if we look at the output that was generated, we'll see a bunch of records. Some of them have TXIDs that are before the 575 and 576 that we saw in our divergent list, because remember, we want to grab a window surrounding the divergence, not just after it. And we have the types of records and so on, the rel file node, so that we can find out what table it's actually involved in. And at the end here on the last couple records, we have CTIDs, which are expressed by Postgres in this paren block number, comma, offset number paren. Now we'll go ahead and start back up our, what was our replica, now primary B. And that way we can query it with another script that will take that information that we've already generated, along with the list, that list of CTIDs and so on, and will actually query that database and give us the actual information, like the actual row data that we care about. And we're still working around the divergence, not just after it. So we see rows that have a primary key and a name. So that's so far good. But we only care about things that happened after the divergence. So we have one final step. And that script will take in both that tuple info that we just looked at, as well as the list of divergent TXIDs, and filter it down by that. So if we look at the divergent tuple data that I generated, and I asked you earlier to remember this insert and update, and now we've reverse engineered our way back to those 2 commands that we ran. So we've been able to reverse engineer our way back from the logs and the PG wall dump output and find the actual 2 changes that occurred on the server, which of course wouldn't have been hard in a table that has like 12 rows. You could diff them by hand, right? But imagine doing this on clusters with terabytes of data and hundreds of tables. And the tooling becomes a little bit more valuable at that point for obvious reasons. So our final step, now that we actually have logical changes that have occurred, is to manually investigate business impact of those conflicts, or if there are any conflicts and so on. Now, while this step is really up to you because only you know your data layout and how it affects your business and if a conflict in a certain table actually matters or if you can just append the records because they're just logging or whatever else, I do want to offer at least this one kind of guiding point, and that is that you probably actually want to investigate both primaries. We've only looked at one. But if one of them has a particularly higher number of changes than the other, that might be, maybe, might be the one that you want to keep around as the long-term primary because there's less divergence to occur. On the other hand, if the other one has like an update to really critical rows, yeah, it's up to you. It's your business data. So we've captured the information necessary to investigate the split brain, given some ideas on how to do it. But at this point, we don't want to sacrifice our ability to have a physical replica and some data safety there. So we want to bring the diverging node back into the cluster. Now, prior to Postgres 9.5, the only way that we could do this is to resync the whole data directory, just like if we were adding an entirely new node to the cluster. And that's safe and correct, but when you have a multi-terabyte database, it takes a very long time regardless of how big your network connection is. And so it's not something we particularly care to have to do. So in Postgres 9.5, there was a utility called PG Rewind added that can help us out in this scenario. Now, according to the docs, the conceptual thing that PG Rewind does is it resets the state of the data directory to the point at which the divergence occurred. Now, I have an asterisk here, and I'll come back to that in a second, because this is not quite correct. It requires a couple of things. Your cluster has to be initialized with data checksums, which you should probably do anyways, but unfortunately that's something you have to do at cluster initialization point, or you can turn wall log hints on, and that would have to be on before the divergence occurred. So do one of these two things, whichever one's possible. The replica also has to be able to access all of the write-ahead log beginning slightly before the divergence. If it doesn't have it available directly on disk, you can provide a restore command that it will use to retrieve it from, say, your backup server or something. PG Rewind also, when it runs, copies all config files. So we'll have to be careful afterwards to make sure that they're correct. I'll mention one particular caveat when we demo this out. It actually this asterisk that I was mentioning earlier, it actually resets data to the divergence point plus any changes on the source primary to the same blocks. And this is because the way that PG Rewind works is that it scans through the wall on the cluster that you're working on. It takes note and tracks all of the blocks that have actually changed, gets the current state of those blocks from the primary that you're pointing it at, and writes them out to disk. And that means that by itself, it doesn't result in an immediately usable node. In fact, it's very plausible that the node is not even internally consistent and may not be able to be safely read from. So after you run PG Rewind, the replica still needs to stream or restore all of the primaries write-ahead log beginning at the divergence point through the current time to be consistent with itself and with the cluster. Now, if you haven't rotated your wall and there's a very small amount of changes, the wall is actually part of syncing that data directory. So when you start Postgres back up, the wall will in fact be replayed. But like I said earlier, it copies all the configuration files, so make sure that you set up a recovery conf file first, or otherwise starting back on the server really just means you've split brained again. Not fun. So let's try it out. So remember we started our server so that we could query from it and find out what had changed. We're going to go ahead and stop Postgres again. And then we're going to run our rewind command. So it tells us that it found a divergence point, which happens to be, I don't know, we can't actually see it, I guess, here. Well, actually, we can see it all the way at the top of the screen, I think. This LSN that it found does, in fact, match the LSN that we found earlier in our log files, this D78. That's the divergence point, and then it actually rewinds to a last common checkpoint, so slightly before that, and put us back on timeline 1. So remember, we don't want to start back up Postgres right now because we will split brain again. And I made the claim earlier that it copies over configuration files, and so we've actually lost something. And I just want to point that out. that if you look for a recovery conf file in your data directory, it's not there anymore. So that's not good. Now, I've stashed away, for the purposes of this talk, a copy of the recovery conf file in the root, assuming that, oh, there's a typo or a space, extra space here in the. So we have our recovery conf file, and let's just make sure that my typo there didn't mess it up. Okay, yeah, so standby mode equals on, and we have a primary connection info. So our recovery conf file is here now. So we can go ahead and start back up the server now safely. So we'll do that. We've started our server. It should have replayed the wall. And if everything has gone well, then we should be able to connect back into our demo database. We should be able to insert into items with a name of, not jinxing myself, but success. And if all goes well, we should see over here we see the row success has replicated back over, and we don't have our extra or wrong row, and the updates have been effectively blown away. So now our what was our replica at the beginning and became a divergent primary is now rewound, it's replayed, it's back into the cluster, and streaming changes from our single primary again. So, in summary, I would argue that your high availability configuration should make split brains impossible, but nothing is impossible with computers and humans. So do it as best you can and know how to fix it if it happens. We were able to use PG Waldump's semi-human readable output format to diagnose what happened after that split brain occurred. And then we were able to use PG Rewind to restore the divergent node to a consistent replica state, and we were able to reintroduce it safely into the cluster and continue streaming on our merry way. So if you have any questions, I'd be happy to take them, and this is the URL for the talk on GitHub. Yes?
So there was that message where it said like the last wall message successfully applied, and then the wall message that diverged. Is the wall message that diverged always going to be like the one after the last one that was successfully applied, or are there cases where they'll be different?
So the question was, in the logging that we saw, it tells us the last record that applied, and then it tells us the one that it errored on. And the question was, well, is that the one that it errored on, or the divergent record, will that always just be the next LSN in the stream, right? Is that a good summary?
Yeah, I guess as part of that, like, what does it mean to, like, to error on it? Because it doesn't actually have that wall record.
Yeah, so if you remember earlier, I kind of glossed over it a little bit, but it tells us in that output the length of the record. So let's say that we had a record at LSN1 and length 50, right? Then at index 1 plus 50 into the stream, you would have the next record. And that's the one that it tries to parse as fails on, and that will always be the next one after that index plus offset, or index plus message length in the wall. So the next one will always be immediately following that. Anyone else? Yes?
So is this something you actually had to do in an emergency situation, or is this?
Yeah, so we knew this question would come up. Yes, and we did write this scripting on the fly, and so I won't argue that it's the best code that I've ever written, but it does work. And so, like I said, human errors do happen. Anyone else? All right, thanks.